All right, so let's get back in the lecture. So you all just got back your exam 1. It's been graded and returned to you. I've also posted all the grades on Blackboard. So I think the attendance is up to date, but don't quote me on that. But on Blackboard, your attendance, your homework, and your exam 1 is all posted, and it's also computing your class average. Again, that's one of the big reasons why I like using Blackboard, is because at any one particular point in time, you can log on and see what your grade is at any time. So your current class average is on Blackboard. Okay, let's talk about homework. So I'm assigning homework for today. It is the first concrete homework. Basically, the way the homework is structured, there's essentially 4 problems from the book. The first 3 problems are essentially snippets of the concrete mix design procedure, and then problem 4 is a full-blown start-to-finish concrete mix design. So between what we do in class, what we do in lab, and what you do on this homework assignment, and obviously your exam, you should have plenty of experience doing concrete mix designs. I also mentioned the class is going to be canceled Tuesday, October 10th, assuming that my flights work out. Last time I had some issues with that, but we should have, hopefully everything will work out. But yeah, we're going to be canceling class on the 10th. On Thursday, we're doing our mix design demo. I don't have this up here, but Thursday we're doing our mix design demo, and then the Thursday after that we are doing our first concrete mix design. I would just I would wear clothes that you don't mind getting a little messy. Not 2 days from now, we're saying 9 days from now, but wear clothes that you don't mind getting a little messy. We are going to be mixing concrete. It can splash. Just be aware of that. Everybody good? Okay. I also, just for the heck of it, I decided to put the results from the mortar cube testing. All in all, the compressive strengths were a little higher than I thought they would be. They ended up being about 3,800 or 3,900 PSI, but the standard deviations were, they were sort of all over the place. So some folks didn't quite tamp their molds as well as they could have. But I bring this data up just to kind of give you an idea of just some, this is some numbers that you can get in this class. And also, I mean, standard deviations were pretty relevant given our concrete mix design procedure that we started to discuss last time. Today, what I'm going to do is I'm going to fully lay out those concrete mix design procedures, start to finish, and then on Thursday, we're going to do a full-blown concrete mix design. Sound good? Yes. Yes. Oh, yes. Because I want to get you all mixing as soon as possible, doing mix design as soon as possible, and plus, because we're not going to be here next Tuesday. So at 12:30, we will be here doing mix design. Sound good? All right. Let's get back into the world of concrete mix design. So here we go. I'm going to go through the first 3 steps a little fast because we've already talked about that in the previous lecture. But just to sort of recap where we're at. So we are going to be discussing a refined mix design procedure that's going to be using volumetric approaches to determine proportions for a given batch of concrete. And our standard is that we are going to be producing a mix design proportion that if all we did is just use those weights, plug and chug, it would produce 1 cubic yard of concrete. So if you need 10 cubic yards, just take all these amounts and multiply them by 10, or so on and so forth. So that's going to sort of be our target. And remember, we're essentially using 3 key pieces of information. We're using the properties of our ingredients, coarse aggregate, fine aggregate, so on and so forth. We're using our intended use and our required our target compressive strength to determine the proportions of the mix. And we'll essentially determine the proportions of the water, the cement, the coarse aggregate, and the admixture and all that. And then we will, using those proportions, back calculate how much fine aggregate we need to attain 1 cubic yard, and then perform moisture corrections at the end. And that's the long and short of it of our procedure. So let's get into it. As we talked about last time, step 1 is to determine our required compressive strength. just looking at the mortar cube data from our lab last week, I think it's fair to say that if we cast, 50, like we got 6 groups, we have 9 cylinders. Let's say if we tested all of them all at once, they're not going to yield the exact same compressive strength. There's going to be some scatter associated with it. So what we will do for our, or what we do for mix design procedures is we say, well, we refer to ACI, which defines the allowable risk for a given mix, is that there's a 10% chance that the compressive strength is less than the target. So go off of your z-scores from a normal distribution, and you find that's 1.34 standard deviations away from the norm. So our required compressive strength in most cases is going to be our target, FC prime, plus 1.34 standard deviations. There's a second check that ACI requires if we have a large standard deviation, which you all saw that was possible. I mean, what do we get from our mortar cubes? It's like 1,300. It's very possible. So we will compute our required compressive strength accordingly. Now this assumes that we're testing at least 30 samples for a given mix. If you're testing fewer samples, you can either A, if you're between 15 and 30 samples, modify your calculation through the use of this modification factor F. And if you have less than 15 samples, there's a pretty simple but pretty conservative plug and chug equation for your FCR prime. Next thing you need to do is determine your target water cement ratio, and what we're going to do is just use historical data that's presented in the text. So based on your target or your required FCR prime and whether or not you're using air-entrained or non-air-entrained concrete, just linearly interpolate to get a target water cement ratio. Sound good? And we talked about this last time, so pretty straightforward. Now, I think we also talked about this. Dependent upon your intended use of your structure, you might be subjected to freeze-thaw cycles. You might be subjected to de-icing salts or seawater or something like that. You might be subjected to sulfates, either through moisture, through soil, or something like that. Based on those intended applications, you have limits on your water cement ratio. Just make sure that whatever you specify falls within those limits. Everybody good on that? And we talked about never adding water at the job site. I know it's happened. Just don't let it. All right? If I find out you said it was a good idea, I'm going to say, come here, stick your hand out. All right. I know I have just, you didn't say it was a good idea, right? Right?
I didn't see anything.
I didn't say that either. Okay. I think this is kind of where we stopped, right? This is kind of where we stopped looking at coarse aggregate. Am I right? Okay. So step 3, okay, so like I said, we're going to start determining the required weights of individual ingredients. And we're going to start with the coarse aggregate. Usually we like large, dense, coarse aggregate. The more coarse aggregate we have, the less other ingredients that we needed. It ends up generating a stronger batch of concrete. The one thing we have to make sure of is that the actual particles, the actual rocks, if you will, in our gravel, you're going to hear me interchange the term coarse aggregate and gravel. You have to make sure that those particles of gravel can actually fit in your form, that they can fit in between the reinforcement, and so on and so forth. So this is the only place in our mix design where we're going to use maximum aggregate size. Remember, if you're going down a sieve analysis, nominal maximum aggregate size is the first sieve going down that retains aggregate. The maximum aggregate size is one size bigger. This is the only place where we use that one size bigger because we're trying to be conservative and we're trying to ensure that those individual particles can fit in your forms and in between the bars and between the bars and the formwork and so on and so forth. Everybody okay with that? Everywhere else we're going to use nominal maximum aggregate size. Everybody good? Okay. I also threw standard sieves, so if you know your nominal maximum aggregate size is 1.5, then the max aggregate is 2. Sound good? Okay. So the way that we determine the weight of coarse aggregate is as follows. Okay. So what we'll end up doing is we'll end up taking our unit weight of coarse aggregate, which is just dry rotted unit weight, just weight per unit volume. That's pretty easy to determine, right? First thing that we do is we take that unit weight and we multiply it by 27, okay? The reason why we multiply it by 27 is because unit weights are typically pounds per cubic foot. I need to know how many pounds per cubic yard, okay? Again, remember, our target for our mix design is going to produce a batch that will occupy 1 cubic yard, okay? But what I am also going to do at this point is recognize that coarse aggregate is not the only aggregate that I'm using in my mix. There's also fine aggregate and there's also sand. And the long and short of it is, dependent upon how fine your sand is, the amount of coarse aggregate that you need is adjusted accordingly. And the long and short of it is, the more fine that your sand is, the more fine your fine aggregate is. Your fine aggregate is able to fill those voids within your concrete, and you don't need as much coarse aggregate. So the way that we measure that is as follows. We say, all right, based on your nominal max aggregate size and your fineness modulus, see, now it's starting to pop up, right? Based on your fineness modulus and your nominal max aggregate size, we adjust how much coarse aggregate goes in the mix. And the idea is, the finer your sand, the less coarse aggregate you need. So if you have a fineness modulus of, let's say, 2.7, we've got values for 2.6 and 2.8 linearly interpolate. Sound good? So the value that you're looking up in this table, we call that C sub S. So you take your unit weight, adjust it for cubic yards, and adjust it by the C sub S term. That'll give you how much coarse aggregate needs to go in a cubic yard. Everybody good so far? Okay. And that's where we stopped, right? I think that's where we stopped? Okay. All right. So this is new. Okay. So step 4, and like I said, we're just taking our ingredients one at a time. The next thing that we're going to determine is air entrainment. And that's one of the biggest, or one of the most important admixtures that we use in concrete applications. Remember, entrapped air is a bad thing. Entrained air is a good thing, especially when you've got concretes that are subjected to freeze-thaw cycles. A little bit of entrained air inside your mix is a good thing. It gives you a little bit of wiggle room during that expansion and contraction under freeze-thaw cycles. Sound good? Now, we're going to need to understand that later, because like I said, when we compute our total amounts in the end, remember, we are producing a mix for 1 cubic yard. So we're computing a mix based on volume. I propose that inside that mix, air is going to take up some amount of that volume. So we're going to have to account for it accordingly. Now, the amount of air entrainment, because we're really talking about freeze-thaw cycles, the amount of air entrainment is a function of your exposure. And so we typically define that into 3 categories. We have mild exposure, which is going to be something that's indoor that really isn't going to be exposed to, or anything that's not going to be exposed to freeze-thaw. So maybe something like a floor slab in this building, or an interior column or beam in this building. This is inside. The temperature is regulated. It's really not going to be subjected to those types of cycles. Moderate freeze-thaw cycles. Moderate freeze-thaw cycles might be looking at something like this column, because this column it's not in the inside of the building, but it's right there on the edge, so it's somewhere in between. Severe exposure to freeze-thaw cycles would be something like a bridge deck or a bridge element. They're completely outside, not protected at all, so air entrainment is definitely going to be necessary for those conditions. Based on your nominal maximum aggregate size and based on your exposure category, you can determine the amount of air entrainment that's going to be required for a given mix. Pretty straightforward. So if you had 1 inch maximum aggregate or nominal maximum aggregate size, you had moderate exposure, you need 4.5% air inside that, or 4.5% air by volume inside that given mix. And that's where air entrainer comes into play. Everybody good so far? Pretty straightforward. Step 5, workability. So everybody in here, I think I've mentioned this already, but everybody in here has heard of a slump test before, right? So a slump test is essentially a generalized measure for determining workability. Okay, so it's kind of funny. Actually, before class today, myself and our lab tech Patrick, we actually went and did a dry run of some of the mix designs that we're going to be doing later. And we didn't do moisture corrections because we were just doing a quick dry run just to make sure all the equipment was working and all that. And because we didn't do moisture corrections, and because we probably had negative free moisture inside our aggregates, nudge, nudge, wink, wink, because we probably had that, what ended up happening was the amount of water that we put in our mix was a lot less than it should have been. Everybody's like, oh, well, you should have just added water at the job site. No. No. Once you do the mix design. But what we ended up finding is we had a mix that was fairly stiff, and our slump was actually pretty low, and so that's something that we can correct down the line. But the long and short of a slump test, just so everybody's aware, is you have a very standardized setup. You have a standardized metallic cone. You fill it up in 3 levels, rod it 25 times, and once you lift that cone from the mold, don't turn it, don't twist it, just lift. The concrete that is inside that cone is going to fall a little bit. The more workable your concrete, the more it's going to fall or slump. Okay, so usually what we'll do is we'll turn the cone upside down, set the tamping rod on the top, and just measure that accordingly. But what we're talking about here at this point in our design procedure, we would like to be able to achieve a given slump within a given mix. Like, for instance, if we proportion the mix, and I proportion it such that it's going to be used for, let's say, a beam or a reinforced wall in the building, well, for those applications, you want a slump somewhere between 4 inches and 1 inch. So hopefully in our mix design, we can actually produce a mix design that actually achieves the slump that we want. Hence, no adding water at the job site. So that's kind of the idea. All right. Everybody okay with this? Yes, sir.
Does that situation apply if you get less than an inch of slump?
Well, with a good mix design, that shouldn't happen. So, but I know
That has happened.
it happens that.
I didn't come that far. It was
The mix design, I mean, hopefully stuff like that is caught beforehand, but well, it depends. That's another point, and that's exactly what we're talking about here. It depends on your application. If you're using, if this is shotcrete or something like that versus, just a sidewalk, it depends on what you're talking about. But yeah, we're getting into a larger discussion. Yeah. And we are going to bring this stuff up later, proper placement, proper handling, and so on and so forth. But I could talk about that all day. I sort of have to stop myself because I all right. Now, in general, we do like the highest slump possible. That's usually what we like, and you're going to see where that comes in here in a second. Let me sort of mention this real quick. So based on your given application, so if this is going to be an application for a beam in a building, based on, because it's a beam, here are essentially our ranges for slump. We want to slump anywhere between 1 to 4 inches. Using that slump range, what we are going to determine is how much water needs to go into the mix. So step 6 is to determine how much water is going to go in, how much weight of water is going to go into the mix. So for a given slump, our water content is going to depend on a few things. It's going to depend on aggregate size. It's going to depend on the shape of aggregates, right? Remember that whole angular, subangular, rounded, subrounded, remember that? Based on the shape of our aggregates, if you have rounded aggregates tend to be more workable, so you don't need as much water. So it's something to keep in mind. And also whether or not we have air and trainer. So this is table 7-8, which, by the way, everybody does have that handout, that sort of formula sheet handout, right? Every one of these tables that you see here are listed in that handout. I changed the formatting up a little bit from last year. Last year there was the formulas and then the tables, and I just sort of kept it in one, it's not like a stream of consciousness, but wanted to keep it all together. Okay. One thing that's worth mentioning, if you notice, like for instance, these entries in the table, see how there's like 207, right, for instance, like right here, we've got 207 and then parentheses 350. Does everybody see that? The first quantity is essentially referring to SI units. What's in parentheses is referring to US units. So unless otherwise stated, we're going to keep things in US units, so use the values that are in parentheses. Sound good? Okay. So based on a target slump and based on a nominal maximum aggregate size and whether or not you're dealing with non-air entrained or air entrained concrete, we can determine the weight of water that would be required for a given mix. Now, a couple things to point out. Number one, this table is only produced for angular aggregates. It's for the worst case scenario. So if you're dealing with sub-rounded or so on and so forth, you would actually decrease the amount of water that you use based on that. Okay? This one's also kind of important. If your slump range, and I'll say it sort of splits one of these rows, go with the larger slump. So like, for instance, you might look up for a beam in a building and your slump range is, 1 to 4 inches. So do you use the 1 to 2 or the 3 to 4? Go with the 3 to 4. Go with the larger slump. In general, we typically desire the larger slump because larger slump is going to mean increased workability, and that's going to be a desirable property for our mix. Everybody okay with that? Just something to keep in mind. That's going to happen on our design example, so just keep that in mind. Now, like I said, everything that's in that table is reported for angular aggregates. If you've got subangular, if you've got rounded, so on and so forth, you can reduce your water content accordingly. So if you have subangular aggregate, you can reduce your water content by 20 pounds per cubic yard. If you have rounded aggregate, 45, so on and so forth. If you're somewhere in between, like you got a little bit angular, a little bit of rounded, just use linear interpolation. Just use a weighted average. Okay. Now, what we've got here is once we're done with step 6, we'll get a weight of water. I propose that is going to be a rough weight of water because we're going to have to correct that down the line for moisture content, moisture correction. Sound good? Okay. Step 7, weight of cement. So if you've got the water-cement ratio and you've got the weight of water, bam. Just take the weight of water divided by your water-cement ratio. There's the weight of your cement. We do have to check against minimums. So for instance, if we've got severe exposure, we have to provide at least 564 pounds per cubic yard. And then based on our flat work requirements, based on our nominal maximum aggregate size, we have limits as well. More often than not, at least with the examples that we're going to be doing in here, that won't be a big deal, but we'll check it and see. It's just one of those checks you have to go for. I also am not really concerned too much right now about underwater applications. You think, well, what underwater applications? Bridge piers, right? If you have a bridge pier in the middle of the Ohio River, you're going to have part of that bridge pier that's underwater. Okay, so in those applications, you might have to provide a little bit more cement just to meet PCA minimum requirements. PCA stands for Portland Cement Association. So, everybody good so far? I know it's a long, drawn-out process. I know. Okay. Step 8, admixtures. I have a formula for air entrainer listed on that sheet for step 8. That formula might seem a little strange. It will make a lot more sense when we go through and when we go through our example. But essentially, the way air entrainers work is they will specify how many fluid ounces will generate 1% air per 100 pounds of cement. So you'll basically take the amount of cement from here, the amount of air that's required, and determine your required amount of admixture. Okay. Everybody good so far? Now, step 9. Determine the weight of fine aggregate. Somebody in here last time mentioned, well, don't you usually proportion concrete, or aren't you ordering concrete to achieve a certain volume? The answer is yes, you are. Okay, and this is where I think that comes into play the best. Up until now, what we've been determining are weights. Weight of water, weight of coarse aggregate, weight of fine aggregate, or weight of cement, so on and so forth. What we're going to do here is this. We're going to take each of those weights, and we're going to back compute a volume. And the way that we do that is we use our unit weight relationship. We say that the volume equals the weight of a given component divided by its unit weight, which is just the specific gravity times the unit weight of water. And so what that's going to do is that's going to say for each one of those ingredients, how much volume does that occupy? And once we determine that, we can determine, well, how much sand, how much fine aggregate would we need to add to that in order to achieve 1 full cubic yard. So that's where we account for the volume component at the end. By the way, if you haven't had fluids yet, unit weight of water, 62.4 pounds per cubic foot. So that's a constant. Everybody okay with that? Well, that's SI. That's SI. I don't believe in the metric system. So I think the whole thing, you're just dividing by 0, the whole thing. It's just one big division by 0. That was a joke, by the way. Okay. Okay, so everybody okay with this? Last thing that we're going to do is perform a moisture correction. When you do all these mix designs and you look at the water that is used to hydrate the cement, what we do is this. We assume that all of the water that is used to hydrate the cement in mix designs is excess water. And what I mean by that is we're assuming that all of the aggregate is at the saturated surface dry condition. Okay? Now remember, what does saturated surface dry mean? It means that all the voids are filled, but the surface is dry. All right? So the aggregate can really retain no more internal moisture. The problem is think about that bin of aggregate in the lab. Do you think that bin of aggregate in the lab right now is at the saturated surface dry condition? I'd say no. In fact, I would say, after our demo today, I would say that aggregate is a little dry. It has negative free moisture. Those voids are not all the way filled. Okay? Because of that, if I just, I don't know what that is. Oh, say yes. It's virus protection, I think. Okay. What was I saying? Oh. If I have an aggregate that's, let's say, too dry, okay, and I just use the water content as is, the weight of water that I previously defined, what's going to happen is this. Some of that water is going to get soaked up into the aggregate. The aggregate's going to sort of act like a sponge, and it's going to soak up some of that aggregate. So the amount of water that we need is going to be less than what we have. So in that scenario, we'd actually have to dump a little bit of extra water into the mix in order to achieve that target water-cement ratio. The same is true of the flip side. Do y'all remember that it was that second lab that we did where it was the first time that we were determining moisture contents, and we had, you know, those 3 bowls of sand, and one of them was like really soggy, and one of them was kind of dry, and one of them was somewhere in the middle? Well, what if you've got a big stockpile of gravel or sand that's been sitting outside? Okay, maybe its moisture content is larger than the saturated surface dry condition. Maybe it has excess moisture. So in other words, if you just dump the original weight of water, you'd be throwing in too much water. Make sense? So what you need to do is you need to perform a moisture correction at the end so that when you actually add water to the mix, once it's all said and done, you've achieved your target water-cement ratio. Everybody okay with that? So what's going to happen is you're going to need to perform a correction to account for the difference between how much moisture you actually have and what's your target moisture content. And it's basically going to be related to the moisture content in the existing condition and then the absorption, the moisture content at saturated surface dry. Everybody okay with that? I know it's a lot of tech and a lot of details, but any questions so far? Last thing, the one last thing that we're going to have to do is if we're correcting the amount, we're going to also have to correct the amount of coarse aggregate that's added as well. We end up adding a little bit more to account for that change in volume because the coarse aggregate is got some moisture in it as well. So your final design, when it's all said and done, your final, hey, here it is, should be this. You should have corrected weights of your coarse aggregate, your fine aggregate, and your water. You should have the weight of the cement. That isn't corrected. That's going to change. And then any admixtures that go into your mix. And that's it. That is your mix design. Yes, sir.
So you do a water correction.
Yes.
Go back and do a coarse aggregate correction.
Yes.
Then you have to do a water correction.
No. I know what you're saying, how you would think it would iterate. No, it doesn't iterate. It closes out right here. I know what you're thinking, but no. Everybody okay with this so far? Now, this is a 10-step process. Technically, there would be a step 11, which is to test your mix, right? Which is what we're going to do in lab. We're going to actually go through and check air content, check slump. We're going to do 7, 14, and 28-day compressive strength tests and what have you. And then, based on your results, adjust it. So yeah. Is this part not on here? Is that part not on there?
On this packet?
Yeah. Okay. I'm sorry. That's something I'll have to correct. Okay. All right. Everybody good so far? Bless you. Okay. Now, a few additional notes. This is just food for thought for later. The workability stuff in Table 7.5, the slump stuff, produces what we'll call average workability. So the way that you should adjust that on the site really is really an adjustment, or the way that you should adjust your mix is to adjust your coarse aggregate, not upping or decreasing your water. It's really your coarse aggregate. So you would essentially increase the coarse aggregate to reduce your slump, or decrease the coarse aggregate to increase your slump. So really what you should be doing is adjusting your coarse aggregate for workability, not your water. But it's just something to keep in mind. Now in step 9, we used a volumetric approach to determine the weight of the fine aggregate. I think that's the more appropriate way, and that's what we're going to be doing for mixed designs in our class. If you open up your textbook and look at Table 710, Table 710 provides a weight approach to do that. I don't really like. I think this is a little better. I think it's more refined. But if you're through your book, you're like, what the heck is Table 710? Table 710 is a way to determine how much sand goes into your mix, but it does it from a weight standpoint. And I think the volume approach is a little more appropriate. Everybody okay with this so far? All right. Let's take a breath. A lot of tech, a lot of details, right? Here's what I'm going to do. I'm going to go through the details of this example, and then I'm actually going to end class a little early because I want what we've talked about today to seep in. I want all these details to fill all the voids.
Then what happens come winter? Our voids will be filled. Yeah.
You said winter, and the first thing I was thinking is like, I got to come up with a Game of Thrones joke or something. We'll just, I don't know. Okay, all right. Okay, what I want to do is I want to go through the details of this example. This example is going to be what we do Thursday, start to finish, okay? This is going to be the focus of our entire class on Thursday. So I'm going to take some time, discuss the parameters, make sure everybody understands this. We'll cancel class early. You all did so good on the exam. You get a little bit of a early break. And then come in on Thursday. We're going to tackle this example start to finish. So, okay, example 9. We're going to design a batch of concrete. We're going to do the mix design for a project, for specifically a bridge deck project. So right off the bat, bridge deck. Okay, let's start thinking about that. That's exterior. That's going to be subjected to freeze-thaw cycles. You think this is going to be air and train? Yes, that's going to be air and train concrete. Okay. We're going to assume that the bridge deck is going to be subjected to freeze-thaw cycles. We're going to assume it's subjected to de-icing salts and sulfates. We're going to assume severe exposure categories for the sulfates. Okay. Now the dimensions. Okay. The minimum dimension is 9 inches. So what we're saying is that the minimum thickness of this deck is 9 inches. That can vary a little bit with deck haunches and things like that. But our minimum dimension is 9 inches. Our minimum cover, so just so you all are aware of what I mean by cover, cover is this. So if I have, you know, let's say here's my concrete deck, so, and let's say that this is 9 inches, and I'm just going to pick some rebar. Let's say, you know, I've got a piece of rebar right here. Cover is that distance, how far the piece of reinforcement is from the edge. Okay, based on given applications, cover requirements can vary. For instance, cover requirements for interior elements are going to be different than cover requirements for exterior elements. And if you've got let's say a bridge pier out in Miami, your cover requirements are going to be even more stringent. What we're saying for this project is that the minimum cover is 2.5 inches. Okay, that's what we're saying for this project. Also, the minimum rebar spacing is also 2.5 inches. These values are important because we need to ensure that the coarse aggregate that we're using is actually going to be even appropriate for this project. I mean, obviously we couldn't use coarse aggregate where the maximum particle size was 6 inches. It couldn't fit in those gaps. You see what I mean? So we have to understand that. Okay. Now for the mix design. Our target compressive strength is 4,000 psi. My goodness, what a popular guy. Okay, for this mix design, we're going to assume a target compressive strength of 4,000 psi. For those of you that have had reinforced concrete design, that was one of the most common values that we used all semester. 4 KSI is very common. Now, that is what the structural engineer assumed for the design of this deck. Okay, that is not what we are going to use for a required compressive strength for our mix. Our required compressive strength is probably going to be something like 4,500 or even larger. Because remember, there's that acceptable risk, right? Remember that you know, if we go test 30 cylinders, there's going to be some that fall below 4,000 psi. So our required compressive strength is going to be a little more stringent. Now, we're going to assume after testing that we have a standard deviation of 400 psi, and we're going to assume that for this project, well over 30 samples are going to be tested. So that's going to make that process a little more straightforward, although we can handle 15 or 30 or anywhere in between. Okay. Everybody got all this? Okay. Properties. So the coarse aggregate for this mix is going to be, we're going to have a 1-inch nominal maximum aggregate size. It's going to be subangular aggregate. Let's look at our data. So our moisture content is 1.69%, and our absorption is 0.51%. So pop quiz, does this aggregate have positive free moisture or negative free moisture? Positive. It has more moisture than it does at the saturated surface dry condition. So our moisture correction that we do at the end, we're actually going to be decreasing the amount of water that goes into the mix, because if we just threw that much water in at the beginning, we'd have too much water. Does that make sense? Right. Our specific gravity, 2.665, that is at the saturated surface dry condition, and our dry rotted unit weight is about 108 pounds per cubic foot. Okay. Portland cement, we're using type 5 Portland cement, which really isn't going to affect our actual mix design very much, but that's important because if you remember, type 5 Portland cement is for exposure to sulfates. So that's going to be appropriate for what we're talking about. Our fine aggregate, the moisture content is 4.5%, and its absorption is only 0.9. So we got some really soggy aggregate, if you will. We're going to have to decrease that moisture or that added water content a fair amount. The specific gravity is 2.599, and its fineness modulus is 2.7. Since this is an exterior application, we are going to need admixture. We're going to use air entrainer, obviously. So just so you understand this delineation, that's 0.1 fluid ounces for 1% air. So if I needed 5% air in my mix, I would need 0.5 fluid ounces for every 100 pounds of cement. So what I'll do is I'll take this, multiply it by my air content, and multiply it by however many multiples of 100 pounds of cement I need, and that'll tell me how much air and trainer I put in. So there we go. Is everybody okay with this? Okay, I'm going to let those values and that data seep in. I threw a lot of tech at you. I'm well aware of that. And I think the only way that you're really going to grasp it, and it's really going to set, concrete set. Yeah. Well, everybody seems down, like they're just all slumping in their chairs, and that was dumb. I'm gonna. All right. Next time, be prepared, start to finish, to attack this example. Everybody okay with that? All right. See you on Thursday.